Thank you for the invitation. So I'll sort of restart a little bit on the last part that Professor Borkar spoke about. So before we get to that, let me just set up some notation and also as a warm-up introduce a Lyapunov function for a very simple case. So let S be a finite set. It's going to be the state space of a continuous time Markov chain. Let L be the rate matrix of this Markov chain that I will describe, which is operating on the state space S. So Lij, the ijth entry of this rate matrix, is going to be the rate for the transition from I to j. We'll assume that this L is irreducible, the Markov chain is irreducible. Lii is such that the row sums are all 0, and that makes this a rate matrix, and it also indicates roughly what the expected holding times are. The inverse of this is the expected holding time. Now, x of t is going to be the Markov chain that we will discuss about. So it's a continuous time Markov chain on the state space. There is some initial condition nu naught. The law of x of t I'm going to denote by eta of t, or t positive, and I will denote it as a column vector. Prefer to use column vector notation. Then we have this forward equation for the law, how it progresses across time. So eta dot of t is equal to the adjoint of this generator L times eta of t. So this describes how the law evolves across time. The initial condition for this ODE is eta of 0 equal to nu 0, the initial distribution. Now, there is a natural Lyapunov function for this dynamics, and that's relative entropy. We saw that in many talks already. So let nu be the invariant measure or the stationary distribution of this continuous time Markov chain. So this continuous time Markov chain is irreducible, so there is a unique invariant measure. Let's call that nu. It's also the resting point of this dynamics. So L star of nu is equal to 0. We saw this in the previous talk as well. Now, the dynamics in our case is not necessarily reversible. So this is a somewhat more general case. So it's well known that relative entropy is a Lyapunov function for this dynamics. What do I mean by that? So relative entropy with respect to the invariant measure, so I'll write this as this function. So this function is given here, I'll come back to that, is a Lyapunov function for the forward equation dynamics. And I mean a Lyapunov function in this sense: if t is greater than s, then the relative entropy between the distribution of the Markov process at time t with respect to nu, the stationary measure, is less than or equal to the relative entropy between the distribution at time at some earlier time and s and nu. So it's descending down, and that's what we will use as a definition of a Lyapunov function. One can say some more things about strict inequality here in some cases, but we'll just stick to this somewhat weaker notion that it's non-increasing the trajectory of the forward equation. So this relative entropy has this formula. It's the expectation with respect to the mu measure. So relative entropy between mu and nu is the expectation with respect to the mu measure of the logarithm of the likelihood ratio between mu and nu. This is something that will come up often, and in fact this particular result we'll see, we'll put to good use. Now the problem I'm interested in is a somewhat different problem than this simple forward equation setting. It's a nonlinear McKean-Vlasov equation. So how do we get this? So the move from the linear equation to the nonlinear equation is that L, which we had, is now replaced by L eta of ij. So it depends on the eta. So here's the McKean-Vlasov equation. Eta dot of t is the adjoint, but L is a function of eta itself, and we evaluate it at the current position, which is eta of t, and then multiply it by eta of t. So this is the dynamics that we are interested in. So L is replaced by L eta, it depends on eta. Now, the question that we were after is, what is a Lyapunov function for this dynamics? Now, for simplicity, let's assume that this dynamics is such that it has a rest point. So the rest point is something that will satisfy this equation. But this rest point, let's assume, is also globally asymptotically stable for the moment. We then know that there is a Lyapunov function. Let's identify an explicit one. How does this McKean-Vlasov equation arise in exactly that way that Professor Borker spoke about? Let's say that there are n interacting particles. The nth particle's state at time t, that's the state of the nth particle, is something that belongs to the state space S. Now, these particles are evolving and there is some interaction. That interaction is a weak interaction. I'll describe what that interaction is. For that, I need to set up some notation about the empirical measure. Let eta n of t be the empirical measure of the system, which is the distribution of the n particles across states at time t. So eta n of t is this empirical measure, 1 over n for each particle's state at time t. Delta is the point mass, Dirac delta at xn of t. So who asked the question? Okay. So this is a vector which is a unit vector with 1 at the location which is xn of t. So you give if xn of t is equal to I, you give a mass 1 for that, and then when you sum it up and divide it by 1 by n, it gets a mass 1 over n. Is that clear? So you just count how many particles are there in state 1, how many are there in state 2, and so this eta n of t is a probability distribution. Yeah, it's a probability delta x. It's just Dirac delta. It's a 1 there at a particular location. Okay. Now the mean field interactions are as follows. The transition rate of a particle depends on its state, but it also depends on the other states, but in a weak way, only through the empirical measure. So the transition rate for a particle in state, let's say a particle is in state I, and let's say it's the nth particle. It's going to evolve across time. The rate at which it will jump from I to j is Lij, but modulated by the empirical measure. You evaluate the L at the current empirical measure, and that's the rate. And so one way to construct this process is to have all of them run a Poisson clock with rate given by the for a particle in state I. You let it run with a Poisson clock, which is whose rate is given by the diagonal negative of the diagonal term. Then when this someone's clock will ring first, when that clock rings, that particle will transition, and the transition to one of the states is given by the weights of each of these with respect to the diagonal term. So that's the interacting particles. Question? Yes. It is possible, but I don't quickly see how to get it with back. But this is one way by which we can realize the McKean-Vlasov equation. It's finite. I'm assuming it's finite. Yes. Also, I think there is a well-definedness issue as well. So everything is nice and simple in our case, finite. Okay, so here are the assumptions and then a limit theorem that tells how the McKean-Vlasov equation arises. So suppose one can prove this under weaker assumptions, but I'll assume this somewhat stronger condition. So if you look at this rate matrix L, eta, as a function of eta, it's lower bounded by rho times some L under bar. So that's basically saying the L under bar is something which has only zeros and ones. So L under bar provides an encoding of what transitions are possible and what transitions are not possible. And this lower bound says that whenever a transition is allowed, it happens at a certain minimum rate across all possible empirical measures. So that's the rho. So that's how one interprets this. So we'll assume this condition. Also, we'll assume that the mapping from eta to L eta ij for a fixed ij is Lipschitz. There are only a finite number of such pairs, so the entire function will also be, so you can find one uniform Lipschitz constant for the entire L. Also, we'll assume that this eta n of 0, which is the empirical measure at time 0, that could potentially be random, we'll assume that it converges to some deterministic measure nu naught in probability. So under these assumptions, we can realize the McKean-Vlasov equation as a limit. So under the above assumptions, we have the following convergence, which is uniform over compacts. This convergence is in probability. If you look at the empirical measure across time, eta n dot, that converges to the solution to the McKean-Vlasov equation. Nu dot is the solution to the McKean-Vlasov equation with the initial condition that comes from where the initial conditions converge to. And so this is one way in which it arises. Okay, so here are some interesting asides. So why was I interested in this problem? So I come from an engineering background. This particular interaction is something that we actually see in Wi-Fi systems. So when particles access a particular medium, they either get the access or they don't get access. When they get access, they move to a state which is a success state. But when they fail, then there is something in the protocol that we have designed which makes it back off and it moves to a new state. And when it moves to a new state, it makes an attempt with a somewhat lower probability in the next time slot. This is a time slotted version, but one can model this as a continuous time system as well. And so successively, as a particular node access as a particular laptop encounters more collisions, it backs off and attempts at lower and lower probabilities. And at some point of time, you just throw away the packet, and then you move back to state 0 and pick up a new packet and tell that you've discarded the packet, that's viewed as success, and then you start operating on the new packet. One can view this actually as a transition of a particular node across various states, and the interactions are one of collisions. When there is a collision, you essentially move to another state. Now, there are some subtleties here, because in the Wi-Fi system, when there is a transition, it's because of a collision and another node also collides at the same time, and therefore two particles move. But in this continuous time Markov chain world, exactly one particle will transit. So there are some nuances, but this is a simplified model of that particular, more nuanced Wi-Fi model. It also arises in many queuing systems. So that's the reason I was interested in this, and maybe I will describe a little bit more about its use subsequently. So if the initial measure is exchangeable, then there are many other interesting things one can say, and I think Professor Borkar also mentioned in the context of interacting diffusions. Asymptotically, each individual particle state is distributed according to nu of t. And this particle, let's say a tagged particle, it evolves according to a time inhomogeneous Markov process, whose transition rates are given by this L nu of t. Okay, so you can actually say that it's in the limit, it evolves according to a Markov process. Asymptotically, the particle evolutions also decouple, and this is termed as propagation of chaos. And it is in this context that we got interested in this, because when these Wi-Fi systems were analyzed, there was a performance analysis methodology which basically made an approximation that each of the particles are evolving independently. And then the analysis involved a certain fixed point equation. It is to make these assumptions rigorous that we were looking at this particular model. If nu is the rest point of the McKean-Vlasov equation, and that's globally asymptotically stable, then the equilibrated distribution of k-tagged particles is a product measure according to nu. So these are interesting asides that one can come up with. Okay, now towards identifying a Lyapunov function for this McKean-Vlasov dynamics, let's look at a somewhat bigger Markov process. Yes?
So this application you mentioned on the
Wi-Fi.
That is boundless condition on this rate function.
Sorry, does it?
The boundless condition on the rate matrix we assumed before.
Yes.
Is that a reasonable assumption?
Yes, it turns out that you can write down in the limit of a large number of nodes that are interacting what exactly the entries of the rate matrix is, and they are bounded away from 0. Some transitions are not allowed. For example, so they're either 0, or when they are positive, they are above a certain lower bound. So certain transitions are not allowed. For example, when I make an attempt and I fail, then I will move to a particular back-off state which is only one more than my previous state. And so the attempt probability or the aggressiveness with which I transmit in the next state is determined by what state I am in. So I can't jump 2 states. I need 2 collisions for that to happen. So some transitions are allowed, some are not. Those which are allowed have a lower bound. Okay, so here is another Markov process, which is essentially the empirical measure itself, its flow across time. One can view that itself as a Markov process. Let me write down what the rate matrix for that is. And so this will help us get to a guess for what the Lyapunov function is, and we'll eventually show that that's indeed the case. So here is the eta n of t flow across time, the empirical measure that flows across time. That's also a Markov process. Its state space, though, is the probability simplex of empirical measures on n particles, which I will denote as delta n of s. So it's a discrete set. As n becomes larger and larger, it gets denser and denser in delta of s, the probability simplex on s. The transition from xi to xi ij, so in our caricature in this particular model, there is exactly one node that can transit from I to j at any time. And so let's look at what change it creates to the state. So xi, if we are in the state xi, we can jump to xi I comma j, which means a particle in state I jump to state j. And so that creates a reduction in the empirical measure of 1 over n in the ith state and an increment of 1 over n in the jth state. And this is the original one. So these are the possible transitions. And this occurs at the following rate. So it must be because of a particle in state I that's transiting. There are a total of n xi I of them. Each one runs a Poisson clock, and the clock corresponding to an ij transition must ring. And so the Poisson clock's rate is L xi of ij, and the rate at which the first one rings is this. And then that node will transit from I to j, or that particle will transit from I to j. So the rate matrix for this Markov process, which is specified here, is this Ln of a transition from xi to xi ij is n xi I multiplied by L xi of ij. So if L bar, the set of allowed transitions, is irreducible, so is this. That's something that one can easily show. Okay, so here is a candidate prelimit Lyapunov function from this, and we will leverage the property that relative entropy is a Lyapunov function for the linear dynamic forward equation. So let's write down the forward equation for this Markov process. So here is eta n of t at time t, the state at time t, but by state I mean the empirical measure at time t, and its law I'm denoting as Pn of t. Now the corresponding forward equation is going to be Pn dot of t equals the adjoint multiplied by Pn of t. What's the initial condition? Pn of 0 is the law of eta n of 0. It could be potentially random, but you have a probability measure on it. Initialize the dynamics with that. Now, by virtue of the fact that the set of allowed transitions is something that makes the chain irreducible, this chain is also irreducible. So invariant measure is unique, and it satisfies this rest point equation. Ln star Pn is 0. Then by the Lyapunov function property of relative entropy for this dynamics, forward equation dynamics, we get that for time t, which is a little later than s, the relative entropy between the distribution Pn of t and Pn is less than or equal to Pn of s and Pn, where Pn is the invariant measure. Okay, one can expand this, and this is what we will get, 1 over, and I'm also normalizing by n. The expression for relative entropy is the expectation with respect to the first measure of the logarithm of the likelihood ratio. Now this is a decreasing function in t, in time, and so I've just written down the left hand side here. 1 over n, expectation of the logarithm of the likelihood ratio. This can be, let's rewrite this in this way so that we are ready to use large deviations. So here is the expectation, and then I pull the 1 over n here and write log of 1 over Pn as minus 1 over n log Pn of xi. So that's this term. And then there is, of course, the second term corresponding to the numerator here. So once you write it in this form, it's sort of clear that there is a natural Lyapunov function. By the limit theorem that I had mentioned, n particles going to infinity, we get the McKean-Vlasov equation. Eta n of t converges to nu of t in probability. What that essentially means is that the Pn of t converges weakly to this point mass at nu of t. So this is essentially a point mass at nu of t. So it concentrates at this particular location. If we can say something about these two quantities, then we are in business. So let's interpolate this. So this is something which takes values in the empirical measures on n particles. So let's interpolate this to get a continuous function on the probability simplex. I'll call that interpolated function j and t. Then similarly, this is for the invariant measure, Pn. This is for the invariant measure. This is for the measure at time t. Similarly, do it for the invariant measure. So these are the two quantities. They are defined only on delta n of s. Let me extend it to delta of s in a continuous way. So this I'm defining as j and t and jm. Now, we know that this converges weakly to this point mass at nu of t. If we can say something about these two functions, in particular jn of t and jn, when we are viewing them as functions on delta of s, if there is uniform convergence, then we can essentially extract a continuous function out of them and then plug them in here, and that should give us the Lyapunov function. So this is what we guarantee from this theorem. So these interpolated functions, j and t is the negative 1 over n of logarithm of Pn of t, but interpolated over this, and jn is for the invariant measure. So these two sequences of functions converge to jt and j. These convergences are uniform, and further jt of nu t is 0. So we'll come to how we use this later. But these two convergences are uniform. And what are the consequences? This is an assertion that we make. What are the consequences? Thanks to this uniform convergence, the prelimit Lyapunov function is as close to the same expression but with the negative 1 over n log substituted by the limiting functions. Similarly here, we can make it as close to this as one wishes for all sufficiently large n. So that's one thing. And also because these functions are continuous, the limit functions are continuous, thanks to continuity, and we have this weak convergence here. J nu of, we can replace these by the integrals with respect to delta nu of t, and so it's just an evaluation of the j at those points. So j nu of t minus jt nu of t is a Lyapunov function. This is decreasing in time. Now this one comes because of the additional property here that jt of nu t is 0. So I'll come to how to argue this very soon, but this is essentially the Lyapunov function. So let me summarize what this is saying, that the function j, which is the large deviation rate function of the sequence of invariant measures, Pn, is a Lyapunov function for the McKean-Vlasov equation. Now, this result was already known. Somehow I had the impression that this must be folklore, but these folk came up with a proof of this in 2015. But I was looking for a somewhat simpler proof, and with Miklo we came with this more, what I feel is a little more appealing and more direct explanation of why this is a Lyapunov function. Now, in an earlier work, Professor Borkar and I, we had looked at large deviations principles for finite horizon, in fact for the empirical measure in path space. And then by contraction to flow of empirical measure, we had computed the rate function, and if you do a further contraction of this at terminal time, you would essentially get the jt as well. And we also looked at the large deviation principle for invariant measure, and that rate function is essentially the j. But the issue was, while we could prove all of these, the kind of properties, the approach that we took was different from the approach that Burker had in his previous talk. And so we couldn't establish continuity, which addresses the question that you also asked. In his case, there was continuity, but the approach that we had could only establish lower semi-continuity. So we had to establish continuity to be able to pass to the limit and use J of nu t as the, use the J as the Lyapunov function. So here's the ingredients that go to prove this result. Now I'll focus only on this Jn to J. And I'll also only give an outline. So the ingredients are the following. So in order to prove this convergence, I actually have to go one more level up. I have to now look at the particles themselves. So here is, let X be the configuration of n particles, the states of n particles at some possible time. So let's call that X. This is a particular configuration. Y is another configuration, but it's a neighboring configuration in the sense that you can move from Y to X via a transition of one particle, or via one particle making a transition. So let mu n of Y, that's also a Markov process. It's a Markov process whose state space is quite large, S to the n. So it has it's also an irreducible Markov chain under the assumption. So it has an invariant, unique invariant measure. Let's call that mu n of Y. This is for the n particle system. So this is the probability mu n. The invariant measure is mu n. So mu n of Y is the probability that the configuration is Y under the invariant measure. So now if Y and X are neighbors with X arising out of a single particle's legal transition, that's the assumption X and Y are neighbors, then we can show the following estimate. If you look at the logarithm of this stationary measure, invariant measure, evaluated at Y, and compare it with its neighboring location, X, in absolute value, it's less than or equal to log n. Okay, so this is something that we could show. And here we crucially use the assumption that the rate matrix is low, all the allowed transitions are lower bounded by some. And it's just a matter of manipulating the equation that defines the invariant measure. Here's the more interesting result. The oscillations of this function log mu n is at most c times n. So that 1 over n log mu n is at most, oscillation of that function is at most c. Now, the first attempt is essentially to use this, to leverage this to come up with a bound like this. But when you leverage this and you think of oscillations, as you pass from, let's say, one corner of your state space to another, you will have to essentially make nodes transit. The number of transitions are essentially n in number, and therefore if you use this, if you try to leverage this, the kind of bound that you will get is n log n. That's not enough. You need your sequence of functions to be bounded. And so for that, we have to essentially do a more intelligent counting of the paths and come up with a better estimate of the oscillation. Therefore, this is something that Laurent Miclot did, and he came up with a bound that essentially said that this is less than or equal to Cn. Once you have this, then you can move from these measures on the space of configurations to the space of empirical measures. And that's just via the following property, that all those configurations which have a particular empirical measure, they all have the same probability distribution. And therefore you can leverage that property to get a bound from, on the ratio of neighboring now configurations in the space of empirical measures on n particles. You can get a bound on such neighboring configurations from a similar bound for the space of configurations. Plus there is a correction factor which thankfully is of the same order as the estimate, so it's c times log n. And the place where this is weakest is near the boundary. That's the location where this ratio is the largest. Anyway, so one gets this bound as well. And using a similar technique and this bound, you can essentially write down the oscillations for the logarithms of the probability station invariant measure for the empirical measures. Once you have these things, it's Arzela-Ascoli that tells you that any limit point must be continuous, and we know that a limit point already exists. So the limit of this, which we know already exists, must be continuous. So that essentially concludes the proof that J is continuous and therefore justifies the limit, and this large deviations rate function is indeed the Lyapunov function. Now, what I will now do is try to give some heuristic description. The rest of the talk, I'll try to give a heuristic description to write down the rate function by inspection in this particular setting. In the diffusion setting, you have norm square coming out in a very natural way. In a very similar natural way, one can write down what the rate function Jt as well as J is by inspection. The formal proof of the LDPs take a somewhat different route. So here's just an outline of the steps that one must go through. So first, an LDP must be shown for the empirical measure over finite horizons in path space. This is via Sarnov's theorem for non-interacting particles, but in path space, and then via an application of the Sarnov transformation. Then one uses the contraction principle to get to the flows. Some additional work is needed here. So these are all things which were already available. But what we were able to contribute is to apply Friedel-Menzel to this context and analyze the invariant measure and show that that also satisfies the FTP. All right, so here's the heuristic way of getting to the cost function. So I'll write down first a running cost of following a particular trajectory, some trajectory eta, which is not the McKean-Vlasov. The McKean-Vlasov path will essentially have a cost of 0. So we are now thinking of going across another trajectory and what's its cost. And then we'll use this to write down the rate function. So here's a possible trajectory, eta of t, and I want to find out what it costs to start from here to go here. And let's assume for concreteness that there is a unique globally asymptotically stable equilibrium for the McKean-Vlasov dynamics, and that's this point. That means all trajectories wherever you start will essentially end up, will approach this particular point. And let's call this nu, and we have some other point here, and eta is this trajectory. Now at each time t, if the current state, if the empirical measure is eta of t, the natural tendency is to go along this particular trajectory. Okay, so the dotted lines are all the natural McKean-Vlasov trajectories, but with different initial conditions along the eta trajectory. And so if you start here, this is the trajectory. If you start here, this is the McKean-Vlasov trajectory. And so the natural tendency is to go along this tangent, the dotted. But follow eta of t, however, the system needs to work against this gradient. So you must follow this against the McKean-Vlasov gradient, move along a different tangent. And that tangent we know, so because we are looking at a particular path, so eta dot of t. So this incurs some running cost, the cost of moving along this direction locally instead of this direction. So that's this Lagrangian evaluated at the current position and the direction along which I should go. Now if this eta dot of t were actually this, then the cost is 0, but we have to move along this direction. Okay, now here are some more heuristics, some non-rigorous arguments to essentially get to the running cost. So let's write eta dot of t as you must go along that direction, along that tangent. So let's think of that tangent as coming as certain rates, some ij transitions. That's given by this GT matrix. Okay, so instead of McKean-Vlasov dynamics, you must have some other dynamics to get to this. That one can write this is something that requires a proof, but can be done. Now, here's another assumption that you're in eta of t, but let's assume that by decoupling the particles' individual states are actually IID with this distribution eta of t. This also requires a justification, but remember that I'm just, for proof, I'm following a different route. For heuristics, I'm following this route. So let's assume that, let's give this to ourselves. So if these are IID, then the natural tendency of these n eta of t of I particles, so the fraction of particles in state I is the evaluation of this vector at I, multiplied by n is the number of particles there. So the natural tendency of these particles, which are in state I, is to have an ij transition at this rate. according to the McKean-Vlasov rate. But we have to move along eta of t. That means they must have an instantaneous rate of gt coming from this matrix of ij. If that's the case, for us to be along this direction, this many Bernoulli random variables, because I'm looking at an infinitesimal time, I can think of these, the number of points there, each node either flipping or not flipping in that dt time. I will look at it as a Bernoulli random variable with parameter L eta ij dt for the ij transition. So there are this many Bernoulli random variables with this parameter. They must have undergone a large deviation to exhibit an empirical measure or a sample mean close to q, not p, q which is gt ij of dt. Now, if you believe all of these things, then we can apply Sarnoff's theorem here, which basically says that these IID random variables have a large deviation principle with rate function given by relative entropy between this Bernoulli and this Bernoulli random variable. And so the negative exponent of this probability is given by this quantity here. How many random variables are there multiplied by the rate function? And this rate function one can expand in this way and recognize that many of the terms are zero, and so the terms which will matter are essentially q log q by t minus q plus p. So this is just a simple calculation that one can do. You sum this over all possible ij transitions and across all time, integrate over t to get the action function. So this is the running cost, and integrate this, that's the cost of the trajectory moving along that direction, which is against the McKean-Vlasov rate. Now, when you have a globally asymptotically stable equilibrium, we can write down what the invariant measure is. So we can write down what the rate function is for the sequence of invariant measures. It comes from this running cost across trajectories, except that we take an infimum over several possibilities. The trajectory's initial condition must be nu, terminal condition must be this xi, and you have as much time as you want to move from nu to xi. And the idea here is that any deviation that puts the system at xi must have started its effort from nu, the globally asymptotically stable equilibrium, and j of nu is 0. So here is a schematic or a cartoon of exactly what the rate function is, but perhaps now I'll employ some of the techniques that you have said to actually compute this for the specific wireless LAN system. So this I came up with to just get the ideas across. So here is the, let's say that I want to find out what the j of nu is. This is something that's familiar for those who are in the large deviations area, but for those who are not familiar, I want to find out what the rate function there is. It's essentially the infimum of costs of paths that start from here and end up there across all possible time. Take the infimum over all possible time duration as well. And so one can specify not just what this j of nu is, but also what's the paths that one would take if one actually sees the state of the system to be near xi. Any deviation that puts the system near xi must have started from nu and must have taken the least cost path. All others are exponentially more expensive. One can do this for the multiple equilibria case as well, and there are multiple stable sets. So here's what happens in the specific wireless LAN setting, where instead of when you back off, each state is progressively more polite than the previous state, and therefore the nodes access with smaller probability. But here is a situation where there are three states. The first two states follow the principle that you have an aggressive transmission at state 0, you have a less aggressive transmission at state 1, but when you have encountered two collisions, then you become super aggressive. And so the number of nodes in the third state, one can try to understand what would happen, what is the distribution at equilibrium. So there are actually two equilibria, one polite equilibrium, where nodes are essentially on this axis you will see the fraction of nodes in state 0, fraction of nodes in state 1, and 1 minus the sum is the fraction of nodes in state 2, which is the impolite state. And so there is a nice equilibrium that's given by this manifold, and that equilibrium is something which distributes the nodes in the first two states alone. But then there is a more stable equilibrium, which is an equilibrium where everyone is impolite. And if you start off the node, if you start off the interaction here, eventually what happens is that you end up at this particular location. So this is a more stable equilibrium. In fact, it was to understand if there are multiple stable equilibria, which one will represent the equilibrated state better in this Wi-Fi setting that we actually looked at all of this. So one can write down what the rate function in this context is. There is this expression here which has an infimum over Vi, but I've run out of time, therefore I'll just summarize. So the large deviation rate function J for the sequence of invariant measures, Pn, for the empirical measure flow, that serves as the local Lyapunov function for the McKean-Vlasov dynamics. And in the event there are multiple stable equilibria, it is the local, it's only a local Lyapunov function. I'll stop there. Thank you.
Systems where you have these McKean-Vlasov systems where you have multiple, let's say two stationary states, you know, where you typically if you have a convex interaction plus double well for each particle, typically you would have many two. So but on the other hand, I mean the interacting replica system would have only one invariant measure because it's a linear system. So with these techniques, can you look at some kind of time scaling in which you understand how you go, because there is a large n goes to infinity and there is a t goes to infinity which should not commute. So is there a way to analyze what is going on with this Lyapunov function approach?
I don't have a, so what you're saying is, if I may paraphrase your question, so look at the double well situation, and you can move from one state to another. Can we analyze using this? Did I paraphrase it correctly?
It's McKean-Vlasov system where you put for each particle a double well potential, yes, plus per interaction, which is convex. And in this case, the McKean-Vlasov limit, the nonlinear Fokker-Planck, if you want, you don't have a unique nu, if you want, in your notation. You have two states, stationary states. But for the interacting replica system, you have only one stationary state because it's linear. So there is something to understand.
In the limit, you essentially get multiple, but for the interacting system, there's always one. So the same thing happens here as well. So if I understood your question correctly, the same thing happens here as well. So I guess if we can extend the analysis to that setting, we might be able to say something. I don't know, I'll have to think about this. But the difference between the particular setting that you mentioned and the one that we had in mind, particularly the Wi-Fi interaction, is the moment you have these double well potentials and interactions, there is some reversibility that's in the dynamics that's available. And so when you have reversibility, you can write down the rate function by inspection almost immediately. Here, there's no reversibility.
So for the case of so just classical McKean-Vlasov diffusion, there is a natural free Lyapunov function, which is very close to entropy. So is your Lyapunov function close to that one? I mean, can you...
For the diffusions?
Yes, that's the first question. And second, in diffusions, you can use that Lyapunov function to show convergence, actually exponential convergence to equilibrium. Can you do something similar here?
So the nature of the function is vastly different. In the diffusions case, the same, I presume that it's also the rate function of the invariant measure. That's why I said that this was probably folklore. When we started on this, I was surprised to see that paper. But anyway, so it's going to be the same. But the nature of the J function, the rate function, is different in the two cases. So here it's quadratic. In the other case, it's going to be, I think it was there in one of the slides, it's going to be, so lambda log lambda by mu minus lambda plus mu. So it's a different function. So if I use this J over in this particular problem, I wonder if it will be a Lyapunov function. But the idea is of getting to the Lyapunov function is the same. So that's the first question. Second question is, can you give exponentially fast convergence rates? We are not yet there. So I suppose so.
You have, I mean, typically what they do is they differentiate entropy, or differentiate the function, get a control on the dissipation, and then they say, with some log Sobolev, I can do stuff.
We actually need that. We need to know what the convergence rates are, because I think the number of, the kinds of numbers that we are dealing with is not 10 to the 23. It's about maybe 100 nodes or so in a large enterprise Wi-Fi system. And so we need to know to what extent we are close to this limit. But surprisingly, if you look at these predictions and the 100 node or 200 node simulations, they're actually quite close. So why is there this fast convergence was the question that was bugging me, and that's why we went to, at least can we show an LDP? So that's the reason why we looked at it. But yes, we need to know what the convergence rates are. I don't know about them yet, but perhaps maybe some others may be able to tell whether there are good results there. But you have a question now?
Yeah. One particle, so that's
Yes.
given by this McKean-Vlasov dynamics, right?
One tag particles empirical, law that will evolve in this way in the limit.
Yeah, okay. So is there any example of M, like this interaction, where one can actually solve these equations in the large deviation limit and find the large deviation function?
Oh, rate function, the explicit rate function. So
yeah.
I think, yes, for example, in the situation where the dynamics is reversible, you can write down the rate function. So here, the characterization of the rate function is in terms of a solution to an optimization problem.
Yeah, yeah. But I want, like,
you want an explicit one. So when the dynamics is reversible, and I think Professor Den Hollander has a paper sometime back in the 90s for reversible settings, both in the case of diffusions and in the case of spin systems, where the expressions are a little more explicit. Dawson and Gardner have a monograph which has reversible setting also addressed, and the rate function is explicit. The moment you have reversibility, you can write down the formulae.
I mean, reversible for each...
the dynamics is reversible. But your question was whether the rate function can be explicitly written.
For the probability distribution for a tag particle.
For a tag, okay, so let me see, you are asking a different question here. The question is?
What I understood is that if I look at the dynamics of a tag particle, that is given by McKean-Vlasov dynamics.
So this is, you're looking for one tag particle and its evolution, and it's exhibiting a deviation. I'm tempted to say that it will be this, but I'll have to think about it. Sorry, maybe we can discuss afterwards.